This is Abby Woe coming to you with my example of an infinite series. And for my example, I chose a telescoping series, which is just a series that allows for the cancellation of all but a finite number of partial sums. So just remember cancellation of partial sums. They're going to be important later, but for now, take a look at my denominator. So I have 4n squared minus 1, and I recognize that can be factored to 2n minus 1 and 2n plus 1. So once I factor it, I split it up into two fractions. We call that decomposing. And so now I use partial fraction decomposition to get our a and b, to find what is in our numerators. So what I do is I just took our original fraction and I factored out the denominator. Then I split it up into two different fractions. And I multiply each one of these three fractions by the factored denominator, 2n minus 1 and 2n plus 1. So that allows me to cancel a lot of terms, and with algebraic reasoning, I result that a is equal to 1/2 and b is equal to negative 1/2. So now that I have my terms, I can just go ahead and plug them in like the format suggests above. I take my 1/2 and put it in over the first fraction. I take my negative 1/2 and put it in over the second fraction. And that leads us to our third step. I don't like the 1/2s in the numerators, so I just kick it out. I factor it out, in other words. So once I factor it out, I'm left with 1/2 times our series. But now, to evaluate the series even further, I have to take the partial sum of the series. And so to do that, I just plug in various values of 1 into these fractions. So I started with 1 because the number that n equals at the bottom of your series notation is the number that you start with. So I started by plugging in 1 to this function. I got out 1. I plugged in 1 to this function and got 1/3. I carried down the subtraction sign, but we know that partial sum is a sum of part of the sequence. And I'm evaluating to the nth term, which means I have to add all of these together to get the partial sum. Now I also started plugging in numbers like n equals n minus 1 down here to get other random values of n. And I recognized that all but two of these terms canceled with our plus and minus signs. And if we add everything up just like it is, all of these terms, except for the first two here, cancel. So I'm left with 1 plus 1 over 2n minus 2. Now, when you have fractions left at this point, the easiest way to evaluate them is just to take the limit as the variable goes to infinity. And we know that the limit of this is 0. So therefore, we're left with 1/2 times 1, which equals 1/2, which proves an amazing fact that you can evaluate an infinite series that's supposed to go on forever and get a finite number. Voila.